In this lecture, I'm going to talk about product of rings. Suppose you have two rings R and S, then you can form a new ring by putting a ring structure on the Cartesian product. And this structure is just component-wise addition and multiplication. So if you have R1 S1 plus R2 S2, it's just going to be R1 plus R2 comma S1 plus S2, and R1 S1 into R2 S2 is just going to be R1 R2 comma S1 S2. It's not difficult to check that this operation will inherit all the ring axioms from the corresponding axioms for R and S. Just to make some things clear, let me give a few examples. So this R cross S has a zero element. The zero element of R cross S is just the zero element of R comma the zero element of S. The unit of R cross S is the unit of R comma the unit of S. And let me just give you a simple example. We've already seen that if we have two integers m and n, then z mod mz cross z mod nz is a group, but it is also a ring under component-wise addition and multiplication. Suppose R and S are two rings, not necessarily commutative. We can form the ring R cross S. And now I ask, what are the left ideals in R cross S? And here's one easy way of constructing a left ideal in R cross S. If I is a left ideal in R and J is a left ideal in S, then I cross J is a left ideal in R cross S. And the proof is really easy. You just have that if A comma B belongs to I cross J, and then you have any element R comma S belongs to R cross S, we need to check that R comma S times A comma B belongs to I cross S. So R comma I cross J. But this by definition is RA comma SB, but RA belongs to I because A belongs to I and I is an ideal. SB belongs to J because B belongs to J and B is an ideal. So this belongs to I cross J. So I cross J is closed under left multiplication by elements in R cross S. Of course, I cross J is also an additive subgroup of R cross S. So I cross J is a left ideal. Now you can replace this left here by also by right or by two-sided, and it works exactly the same way. And here it will be a right ideal or a two-sided ideal. So if I and J are right ideals in R and S respectively, then I cross J is a right ideal in R cross S. And if I and J are two-sided ideals in R cross S respectively, R and S respectively, then I cross J is a two-sided ideal in R cross S. It turns out that every left ideal of R cross S is of the form I cross J, where I is a left ideal of R and J is a left ideal of S. So how do we prove this? Well, so starting with a left ideal in R cross S, we'll try to identify what I and j would be. So let I just be the set of all a in R such that a comma 0 belongs to k, and let j be the set of all b in S such that 0 comma b belongs to k. Now it's not hard to see that I and j are left ideals of R and S respectively, because if you take any element R of R and look at R times A in R, then R times A comma 0 will also be in K, because it is R times 1, R comma 1 times A comma 0. So R and I and J will both be left ideals in R and S respectively. Now what I want to show is that K is equal to I cross J. So it's very easy to show that I cross J is contained in K, because if A comma B belongs to I cross J, then A comma 0 belongs to I, and 0 comma B belongs to K, and 0 comma B also belongs to K, which implies that A comma 0 plus 0 comma B belongs to K, because an ideal has to be closed under addition, which implies that A comma B belongs to K, which shows that I cross J is contained in K. For the converse, if A comma B is in K, then we can take 1 of R comma 0 times A comma B. This is also in K, because K is a left ideal, but this is equal to A comma 0, and this is in K, which implies that A is in I. Similarly, you can show that B is in G, which implies that A comma B is in I cross J, and hence we have that K is contained in I cross J. So K is equal to I cross J. So what we have seen is that if you take a product of two rings, then all the left ideals of that product are products of left ideals of the two rings themselves. The same holds for right ideals or for two-sided ideals.